Hello everyone, my name is Caroline. I'm based in the UK, but I travel all over the world. My mission in life is to make maths fun, to make maths a joyful experience for every child on earth. And to do that, every adult on earth also has to enjoy it to spread that to the children. So I work with Tony. Tony has the maths expertise, and I'm really good at finding the fun things to do. And I use soap bubbles and balloons when I'm performing on stage.
I'm John, or Jonathan, whichever you prefer. I've just finished my degree in maths in Edinburgh, and I'm based in Scotland. And I just have a really big interest in maths education and teaching, and it's something I want to kind of carry on forward past my degree. And I'm just here to help out, just answer any questions I can.
Great, thanks, Jonathan. Okay, I'm Tony. If you know the website, the organisation Enrich, which is based in Cambridge here, I started that in 1995, quite a long time ago. And then in 2002-3, that year, I went to South Africa and helped set up Aims. And you see the little map of Africa with the rays on the left-hand top corner of this slide. That's our symbol. We're a network of higher education institutes where the students are doing master's degrees and research. But alongside that, my field is maths education. So many of you know me through Aimsec, and which I set up in 2003. All my life, I've been I've spent many, many years as a school teacher in the classroom and many years working in university. I'm going to now introduce Trifold. This is the name of the collection of activities we'll do today, but they're all from taking a triangle and folding the triangle. And there's so much maths that you can learn from this. It's, I think you're going to enjoy it. It's what we call a rich activity. Now, you need the things that are in the blue box there. So if you're going to actually do the activities, maths is not a spectator sport, okay? It's a sport in which, it's more than that, but we want you to engage. You have to engage with it if you're going to learn, and that goes for your children that you work with, your students too. And so we hope your lessons start with the students doing some maths themselves, and then they talk about it afterwards, and then only then do you start giving the explanations and introducing them to the new maths you want them to learn. So that's a bit about the method of teaching, but what are we going to do today? Well, you're going to make a few simple folds in your triangles. You're going to work through some practical activities that will help your students to discover for themselves some geometrical properties, some important geometry properties. And in addition to that, you're going to get involved with reflections and enlargements, transformations, and you're going to investigate proofs of geometry theorems, some important geometry theorems that are the part of every school's curriculum. So there you are, that's the program. Now here, this says a lot about our philosophy of teaching, our style of teaching at Aimsec. We're building skills and understanding, not just teaching children and students so that they have some knowledge there. The skills and understanding are hugely important. And when a baby opens its eyes and sees the world out there and eventually sits up, even before it sits up, it's learning. It's learning so much about language, communication, and then it learns to walk. And do we teach babies to talk and to walk? No. They're expert learners, probably better learners than anybody else, okay? So from cradle to grave, we are all learning, and we're on a spiral pathway. And as we get older and go up and up, we revisit ideas that we've met before and we come to understand them better. So in school as teachers, we should be building for the students an experience which will prepare them for lifelong learning and learning the new skills that they'll need in the changing job market and world out there. So that is our philosophy, or a picture that sort of depicts what we believe. And here you'll see a spiral again. I've been studying some different school curricula, and what I see is year after year, the same topics come up in your school curriculum, but the children are supposed to learn to expand their knowledge and understanding each time they revisit the same topic. So from preschool right through to school leaving year, the spiral revisits the ideas again and again, and it continues on beyond school. Now, I want to tell you what Aimsec has to offer. We have a website which we call the Aiming High website. We also call it a teacher network because it's there for you to comment on these learning packs as well. And we really are happy when teachers ask questions or make comments about the learning packs. And the learning packs are a collection of resources for teachers, for this sort of teaching, okay? Now they're available free, no charge for anything, under a Creative Commons license. What that means is that you can copy and paste, you download these PDFs, you can copy and paste and use whatever you want to use from Aimsec, from Aiming High. You're welcome to. We hope you'll acknowledge where you found it, the source, and that's just good etiquette. And we don't. The license doesn't allow you to make a profit out of it. Okay. Now, for lessons,
we do encourage you to share them with other teachers if you find them useful. We encourage you to share them with other people, and so that more people can take advantage of them and spread the learning.
Absolutely. Now, for lessons in school, Aimsec offers resources, and they provide activities for the style of learning we're describing, for differentiation and inclusion as well. So if in your class in Africa, you may typically have 60 students, learners, and they will usually be of different attainment levels. Some of them will be really, really getting on with the maths really well, really motivated, and others will be struggling with maths you're trying to teach. And so what Aimsec offers you is for the same lesson, for the same idea that you need to teach that day, it will offer you an activity that will suit the majority of your class, along with some activities for those learners who are struggling, something simple, which will, important note and connected, where they will have some success and get more confidence and then go on to the things that the other learners are doing. And it won't look different. They won't be sort of singled out because, as having to be given something for the slow learners. They will make progress in the lesson and have an experience of success. Now, it's really bad idea that the high flyers should have to just do more and more of the same. So what we give you also is challenges which are taking the high flyers beyond, and so they can, not with more new knowledge, but using that same knowledge in a more challenging way. So that's suiting giving every learner in the class exactly what they need individually, and that's differentiation and inclusion.
I heard it described recently that everyone can get on, in our case, the spiral, no matter what level you're at, and everyone can get stuck. So it's accessible to everyone, but you can get up the level so that everyone can get stuck and therefore be challenged. And this is a great help to teachers as well, and any of you that are volunteers that aren't necessarily a qualified teacher, because you can use these activities and you can start at the very beginning and just go work your way up the spiral with each of the inclusion guides, and you can learn and get up to speed by using these guides.
Absolutely. And when we're talking about this challenge, it's so that the learners make progress, so that they actually move along this learning path and make some progress, and then feel really satisfied, not without a struggle very often. You know, it's good for you to struggle with the maths, as I often find out.
You get a huge sense of satisfaction. There is no other sense of satisfaction that you get from really getting your teeth into a problem and finally solving it. It's like, whoa!
About a year ago, Caroline and I started writing these inclusion and home learning guides, because so many families were now, because of COVID, different parts of the world, all the children were at home, and very often the family felt, you know, out of touch with the school, and wanted to do something at home. So these home learning guides are designed for mixed age groups. So all the children at home can work together on a starter that everybody can do and be involved in, whether they're 4 years old or 18 years old or whatever age, on the same mathematical theme, and then age appropriate learning activities for everyone. So a collection of different activities for different stages and age groups. And they're now available. They're called, and we're producing more all the time on the Aiming High website. They're called the Inclusion and Home Learning Guides. So we hope you'll find that useful.
So we're reviewing the spiral activity, planting the seeds, cultivating, and what we're doing with the younger learners is it's about gaining the skills, gaining the visualization skills, experiencing the mathematics without the technicalities, without the academic aspect of it, so that when you get up to another level, now we do actually have someone on here that's now at that level. Leon's here, who's 13, and he's now working at the level where he needs what he learned in primary school to be able to go up to the next level with the abstract thinking. Every single level is important, and in secondary school you're then taking that basic understanding, the foundation that was built in primary school, and you've already on the journey of lifelong learning. And now where Jonathan is now, he's just finishing his degree and he's just embarking on another learning journey after finishing his degree. And so we want to start that at a very early age. And what you want to do with a picture like this is just start by, what can you see? What you're looking at a picture, what can you see? What can you talk about? Are you and if you're not, say, have you got any triangles that look the same as each other? Are they different to each other? What are the similarities? What are the differences? Get them to color them in, get them to make it, get them to fold it, get them to experience it, as well as looking at it in a picture, and just have a really good discussion, get everyone's teeth into it, and then share the ideas. This is early years, and what we want the early years children to do is play. It's definitely not about learning shapes. It definitely isn't academic. Provide a bunch of triangles and then ask them to fold the triangle. Make one fold. And then what do you see? Have you made any different shapes? Now what's changed? How many sides has it got? Just be asking questions. Folded it in half. Is it half? is it the same amount of paper on this side as there is on this side? So many questions. What about if you make 2 folds? Take 1 triangle, and using folds, can you make 3 triangles? It gets them to really notice the difference between a quadrilateral and a triangle. It's noticing the properties of shapes. You want them to be observing these things, and you want them to care about them. And what better way to start caring about them than by treating them as toys? What is the same and what is different about all the different shapes that you make? Does it matter? And what shaped triangle you start with?
And when you are given some mathematics, or when you find some maths you want to do, the best start, whether you're 80 something like me, or whether you're 5 or 6, is to start with playing with the idea, perhaps making some sketches, and just play, free play, but particularly for the little ones. And it shouldn't be anything for the preschoolers that's really forced on them. It should be what they are enjoying, and you can leave it if they're not enjoying it. So we think there's a lot to be learned from simply playing with mathematics. And this can be quite a serious pursuit, actually, because you learn a lot from play.
And then you can stick your samples, stick the ideas you've had on a poster, and you can colour all the different shapes in, give them the actual name, and just have a poster that's a constant, they can constantly go back to and be proud of.
And now we're talking to grown-ups, and you might be teachers, you might be parents. I mean, even if you're teachers, this might be something you do from time to time with your own children. You might have preschool age children, and they might have some fun with triangles, as Caroline's just been describing. So what we're talking about is free play with some talk about shapes and very little formal teaching. But what you're doing is expanding their vocabulary, and of course, young children are learning new words all the time. It's not essential that they learn the words, but if they get the experience, that's great. It's learning about different types of triangle and different quadrilaterals. The formal learning will come later when the children are older. But talk with the children about the shapes they make. Ask questions to encourage them to talk about quadrilaterals. If they happen to fold their shape, their triangle, into, they can see a quadrilateral. What is it? What is that shape? What can you say about it? Oh, it's got 4 sides. So we call it a quadrilateral. Give them the names. If they make any of the special quadrilaterals, then you can give them the names. You can call it a rectangle, or a kite, or a trapezium, whatever. Squares, whatever. And ask this question. This is a brilliant question about, you can use in the maths classroom over and over again. What's the same and what's different about the shapes? Or what's the same and what's the different about these numbers? Whatever. It's a really good question. Here's the same activity that can be directed to making named shapes. Now we're coming up to years 3 to 5. So we're up to age sort of 9 years old, or maybe 10, depending on the year groups in your system. And here, the idea is to take the special quadrilaterals and ask the learners to find these special quadrilaterals one by one and show the pictures. So, for example, I might show the class a square and say, can you make a square from that triangle by folding it? And ask them, how many folds did they make? Ask them to explain how they did it, and ask them, what's the shape of the bit of the triangle that sticks out? So that's one I just done, and you can see that the square has been folded, and I started off with a triangle. Now we might ask them to make rectangles, kites, rhombuses, parallelograms, trapezia, I mean. Okay.
You say okay, but this is actually challenging for me. So It's a lovely exercise, and I would be encouraging people of all different ages to do this, and then having the conversation about what shapes you're making. It's a surprise. And also a sense of pride when you do succeed in making the shape you're attempting to make.
Yes, and you should ask questions to encourage the learners to talk about the quadrilaterals and their properties. Whereas with the younger learners, you will only talk about a trapezium if they happen to have made one. Now, as they get a bit older, you'll say to them, I want you to make a shape like this by folding your triangle. And so on with the other quadrilaterals. So learning about the different quadrilaterals by the time you're 9 or 10 and knowing their names is quite important. And now we're going to show you how to halve a line segment by folding. And Caroline's going to demonstrate this. So get a piece of paper ready and mark 2 points on the edge of the paper, A and B. It doesn't have to be at the corner. A doesn't have to be at the corner. Okay. Mark 2 points on the edge. AB is a line segment, and you're going to, Caroline's showing you what she's doing. You're going to make a fold that will enable you to mark the midpoint of the line segment.
I'm making big dots here. For precision, you want to just make a very small line, but I'm making big dots so you can see what I'm doing.
And notice Caroline's using scrap paper. We believe in scrap paper, yes, not wasting paper. Now Caroline's going to mark the fold line. So, and she's also going to mark that midpoint and on the edge there. And we're showing you a technique that's going to be used several times this afternoon. The same folding method works for halving any line segment. And if your line segment's in the middle of the sheet of paper, then it's a bit awkward. Once you begin to fold it, you lose sight of the points themselves. So we suggest you prick a hole through the points, and then you can make them match each other. That's what the word align means. You can make them match each other when folding. So it's not necessarily for the points on the edge of the paper. It also works for any line segment. Okay. And the more accurate you are, the better the results in the end in terms of what you're going to discover. Now, this is the second of our techniques that Caroline is going to show you. You just now take a triangle that you've got ready and cut out, and we're going to show you how to draw it doesn't need to be a triangle, you can do it on any piece of paper. We're going to draw a perpendicular from some point that's not on the line. We're going to drop a perpendicular from the point to the line, okay? So mark some point on that edge.
If you notice, I have chosen a place that's quite close to the apex because I specifically, it doesn't have to be the midpoint. It can be any point.
And also, you don't have to follow exactly what Caroline's doing in terms of, it can be anywhere along that edge.
You can be creative. Choose your own point P.
And Caroline is also going to mark the angles at B and C. It could be an angle that's marked there. It could be just the point B and C, okay? And now she's going to fold, make a fold that goes through P, and she's going to keep B on the line BC, and she's going to carefully make that fold with B still sitting along that baseline, and the fold is going to go through P. So we're going to pause.
Again, I've made big dot for P. You just want to make a very light dash so that you know exactly where P is. My big dot so that you can see it.
So now draw the fold line and mark the point on the line, the baseline BC, mark that. We're calling that S. Give you a moment to do that yourselves. So what you've drawn, well, what you've made is perpendicular from a point to a line segment. So what do you notice about the angles PSB and PSC? Explain your ideas. Now, it may seem very obvious to you, this question, the answer to this question, the angles PSB and PSC.
Yeah, it's not a trick question at all.
No, not at all.
What is the angle PSB and the angle PSC? It's not a trick question, but what we're doing is we're demonstrating how you can present this to your young learners. And it's a really beautiful systematic way of doing it so that you're building on the experience.
And so what we're saying to you is you must, as teachers, ask your learners to explain their ideas. I never accept, or try not to accept, an answer from a student, whether that a student is in a school classroom or university lecture hall or whatever. If the student gives an answer, I expect them to give me the reason for that answer. Okay, if they tell me the answer is 29, I'm still waiting for the rest of the answer, which is why it's 29. Okay, so now, if they really understand the mathematics, then they're going to give a reason, and the other students will learn from the reason. If they didn't know why the answer was 29, then it wouldn't be much benefit, would it? So it might benefit the student who's given the right answer. But what we are impressing on you is that we want you to ask the people you teach to explain their answers, to give you reasons, and then other students will learn from them. The one who's given the answer will be developing their communication skills. It's all good.
So Thelma is saying that the angles are 90 degrees. So the next question that Tony's asking is why? Can somebody just give us, it's a simple question. It's not a trick question. We're just modeling how you would present it.
So Emma has said because you're dividing 180 degrees in two.
And those angles are equal. Why? The idea is that the folding has given you this perpendicular, and we now understand why. Okay, so this is the investigation, and we're going to start by Caroline demonstrating these first 3 steps for you to actually do this investigation and see what you can find out and think, if you want to, about how you would use this in teaching. So take a triangle, and we first of all want to make a fold to find and mark the midpoint P of AB.
This time we are going to the midpoint. Last time it was any point. This time we are literally folding in half, which is going to give us 2 90-degree angles.
Okay,
and finding the point P.
Yes, and now find and mark the midpoint Q of AC. And now fold along PQ.
If you fold it over a ruler like this, you get a nice sharp fold just where it's supposed to be, instead of struggling to find it.
No, we're not going to say what happens to the point A now. We hope you will notice this for yourselves to do the investigation. We want you to write comments, questions and answers.
Starting with what happens to point A. So if you can go through those questions and make your comments and take pictures of what you're doing.
We're going to leave it to you at your own pace to do these folds, make these observations, find out, well, we hope quite a lot, and give us some answers. There's some questions there. We want you to find all the right angles, and we want you to tell us how you know they're right angles. We're asking what shape is PSTQ, but not just to say obviously it's the something or other, but how do you know? Okay, so there's quite a lot of questions there, and that is going to lead us into proving some geometry theorems. Pam is saying, amazing how we can see so much symmetry in such an irregular triangle. Now, while you're doing this, I'm sure you're all interested in teaching in some aspect or some way or other. It could be with your own, playing with maths with your own kids at home, or it could be as a teacher. So please think about it in terms of how you would do this sort of activity with children, how they would do it, what they would get out of it, as well as what you're actually finding. I often say to people, you're wearing two hats when you're with me. One hat is your hat as a learner, doing something that you haven't done before, and you haven't seen exactly this sort of thing before. And your hat as a teacher, as when you're thinking, how would other people learn from this?
This might be a good time, Jonathan, to mention Mary's comment about the variation and your response and your...
Yes, well, Mary's earlier on said some quite interesting things here. She said, an interesting question to older children would be, suppose we don't keep B on BC when we do this folding. Then John replied,
if we instead also place B on AC instead.
Yes, of course, we might have had the triangle turned round in a different way. And then it could be that when you were doing these perpendiculars, they drop down outside the triangle, not just inside the triangle. So there's all sorts of different things that can happen. I love this comment from Pam. She says, 3 hats I am wearing. Learner, teacher, and mathematician. I love it.
We are all mathematicians. We're just at a different part of the journey. Some of us are at the bottom of the spiral. So we are all mathematicians, learners, and teachers in some area. And if we keep that philosophy in life, especially if we are helping young people learn, then we are modeling what those young people need to see in order to succeed.
Yes, that's absolutely right. It's all that and more. What we want children in school to experience is that they are not just doing the homework because they'll get into trouble if they don't do it. They're not copying it from another learner so that they can give in the homework and get the ticks. They're not doing it for the mark in the exam. Ideally, they're doing it because it's an enjoyable experience. Even the struggle that they have to understand something, even the difficulties that they have are worth the effort, because at the end of the day, there's such a lot of pleasure in actually breaking through. That's what it means to be a mathematician. And so, I mean, some people define the word mathematician quite differently. They say a mathematician has to be somebody who proves new results that nobody's ever found before. But that's not true in my head. If a 10-year-old finds discovers for themselves something that they didn't know. Okay, it's a new discovery, and they're being a mathematician, even if other people have made that discovery millions of times.
One from Pam about a multi-decker train idea. To explain the learning spiral, the train will pass by the same platform every day at the scheduled time, and that each of the students can jump on it at a different level as I take them on the journey to whatever the learning intention is. Which is an interesting idea, metaphor. And then I suggested that PSTQ is a rectangle because the opposite sides are equal and parallel. They're parallel because they cannot join.
And number 7 says to check that the lengths PS, XR, and QT are all the same by just bending the paper until the line segments coincide. So that you can check that they are the same. And that's really important. We've been talking about and doing activities that you can use in primary school, and now we're going to move up to activities that we can use in secondary school. And we want to look at what happens if we make 3 folds on PQ, on PS, and on QT, as in the diagram. What happens? And what does this tell you about the angles A, B, and C? What have you seen? Will you please put what you have observed here on the chat line? Fold along the triangle that you were using, fold it along PQ, PS, and QT. What happens?
We've got a response from Emma saying it proves the 3 angles of a triangle are 180 degrees. Just see if we can get any more explanation of why that's a proof.
And Rebecca said, I'm inspired to do some of the practical ideas with my year 1 class and have set some time aside for this. So Caroline's coloured her triangle, so you might like to do some colouring as well. It's often said that you know, in secondary school teachers and learners may think, oh, you know, the playing with the manipulatives, folding paper, that's for the babies, we don't do that. Well, what a pity. How much they're being deprived, because here in secondary school, and even for 16, 17-year-olds, there's a lot to learn from this one activity. So you might introduce it in the lesson in a slightly different way. You may, you know, but it is the same, essentially the same activity. And this proves that the angles of a triangle add up to 180 degrees. Isn't that amazing? And I know there are ways that teachers demonstrated at secondary school, but this is a very convincing way to show it, that these 3 points meet at R, the base of the altitude from A to the baseline. Why does it happen? And just exploring all the reasons there, you're going to learn so much. Isn't this rich? Why I named Enrich was a play on words again, and the letters also stand for something, but we call rich activities one where the same activity has a lot of hidden depths and interesting things that you can find out from the same exercise. Caroline's actually done the activity there where she's divided her triangle into, by folding, into a quadrilateral and 2 triangles. This is preparing us for yet a different discovery. And here we're going to fold along the line PS. And what does that tell you about the lengths BS and SR? So we're exploring now the ideas of lengths, okay? BS and SR. And then fold along QT. What does that tell you about the lengths CT and TR? Now, putting those 2 ideas together, what does this tell you about the length ST? you can see that ST is half the length of BC. Now fold along PQ. What does this tell you about AX and XR? So what we saw was that A would come down to touch the baseline at R, and the other two vertices would meet at R. So AX and XR are equal. And what can you say now about the lines PQ and BC? So we're going to move on now to the area of a triangle. And of course, this is well known, but how many of your students in secondary school can prove that the area of a triangle is half the base times the height?
Never mind prove it, Tony. How many remember it? And
now,
this is really memorable.
What I would do is to get the children, having done this, to stick it in their book and then fold with they can open the flaps and fold the flaps down in their workbook. Way that's most often used, which is a very good way to prove this area formula for the triangle, is to box it in. Most of you will know what I'm talking about there. Just to, to draw a box which into which the triangle fits, and then you can see you can prove this formula. The length of ST, as we just saw, is half the length of the base, and the length of XR is half the height of the triangle. And the area of that rectangle then is ST times XR, which we've seen as the height, same as all the way across. XR, PS, and QT are all equal. Okay, so the area of the rectangle is the length of ST times the height XR, and we know what they are. Okay, so the next thing to say is to put that in on the next line, that's half the base times half the height of the triangle, which is a quarter of the base times the height of the triangle, but that's the rectangle. Now to get the area of the triangle, look at the colored picture there and remember what you did, right? The flaps fold down so that rectangle is covered twice from the paper that made the triangle, right? So the area of the triangle is twice the area of the rectangle. Well, you got half times a half before, which gives you a quarter. Leon, I know you're learning about fractions.
He's learning about area this week, area of a triangle this week.
And so 2 times a quarter is a half. And so now the area of the rectangle was a quarter the base times the height, but that was only the rectangle. The area of the triangle is 2 times a quarter, which is a half the base times the height. So for most people, that will be a new proof of this formula. Okay, so what we've done is the angles of a triangle add up to 180 degrees, and the area is a half the base times the height of the triangle. Now we're going to move on to something else. We're going to move on to what we call transformations, which again is part of the school syllabus in most countries. So when you look in a mirror, you see a reflection of yourself, a mirror image. And we want you to look at, we want you to color the triangle. So we want you to color APQ, which you see green here, and its mirror image. And imagine, well, you should see it in the diagram. You should see its mirror image, and you should imagine a mirror line there, also called axis of symmetry. The orange one, we want you to color not just as you see it in the picture, but it's as its mirror image as well. Think about the mirror line. And we want you to do the same with triangle QTC.
We want to visually see that symmetry, so it doesn't have to be perfect. Thank goodness, because making it perfect, that will be a struggle for me.
And one thing about this colouring that occurs to me, if you can put posters on your classroom wall, it's a really good way to remind children of what they have learned. And if there are big words, remind them that they need to learn the mathematical words. They can go on the poster too. So with this sort of activity, the children can make a poster for the classroom wall. And they love to see their own work on the wall as well. But this helps them to remember what they've learned. What you should have been able to do is to do those, the colouring and to see the mirror images. But here we're looking at reflections in a mirror line, and we're looking at congruent triangles. So the triangle BPR is now made up of two triangles which are congruent to each other. And the triangle QRC, again, it's an isosceles triangle. And there's lots to say about, isn't there? Somebody else earlier on remarked about the symmetry here. And now this is exactly what we're talking about.
We've got a comment from Pam to say that it's, especially if she works in an international school, so just like a lot of the people in Africa, the language is not necessarily the language that they speak at home, the language of instruction, and the just hearing it or seeing it on the board is not the same as actually acting it out and doing it themselves.
Yes.
As you're talking about it. And this is really powerful.
And then we've got here what's the really key and most important thing about this slide is congruency. And you see the congruency of the triangles on the right-hand picture, which we used before in different ways, but now we're using it again to show congruency. How the two triangles that are now on top of each other, the two orange ones, two green ones, and the two pink ones are actually congruent triangles, equal in all respects, lengths equal, angles equal, that's congruency. Now we're going to go on to similar triangles. Now here, the idea is enlargements. Enlargements and similar triangles by folding again. Look at triangle APQ in this diagram, right? It's enlarged from the center A so that the image points are twice the distance from A. That twice the distance gives a scale factor 2. What would the image be with that enlargement? Now there's all sorts of analogies here with 3 dimensions, but we're doing this in 2 dimensions. So we're all very used to seeing images on a screen. In fact, you're looking at me and Caroline and all of this on a screen, okay? And we're small on that screen. We're not life size. Okay, projecting an image on a screen is similar, but it's the same sort of process, but it's in 3D. Here we're looking at 2D. So can you see what the enlargement of triangle APQ is by a scale factor 2? And now can you see the enlargement of the triangle BPS? Remember, you can put your answers on the chat line if you want to. What's the enlargement of BPS? Your children can do this. Having their own triangle to play with in their hands and to experiment with and to think about. And find another triangle in the picture that has an enlarged image. Describe the pairs of similar triangles that you can see in the diagram.
And you can describe them with respect to the 3 letters that describe the triangle. So you've got APQ. What 3 letters are the enlargement of APQ? What 3 letters are the enlargement of BPS? And see if you can find at least one more.
And then, of course, what you're doing is thinking about it, enlargements as making bigger. So APQ has an image ABC, BPS has an image BAR, and CQT has an image CAR, okay? But that's by scale factor 2. What about scale factor 1/2? Think of the same diagram. Because you can shrink things, that's the English language word, and make them smaller. And it's still called an enlargement in mathematics. There's a question there. How does the number relate to the scale factor? That's something to think about. It's what happens. Another thing we can ask about it here is, where is the center of enlargement? And if it's done by projecting an image on a screen, it will be a light source, a single point. The center of enlargement for APQ and AB being enlarged to ABC is the center A. Now, Pam says we had point X at the intersection of AR and PQ earlier, and that helps further. Okay, so AX goes to AR, the point X goes to the point R with this enlargement. That's helpful, Pam, thank you. So when we enlarge triangle BPS to BAR, B is the center of enlargement. So if you describe an enlargement, you need to give the center as well as the scale factor. And scale factor is a whole new story, isn't it? It's such an important idea in mathematics. Going back into the maths classroom, similar triangles is something children have to learn about. And enlargements and similar triangles are all the same maths, really. You know, it really is all connected, a connected idea. Just as we connected reflection and congruent triangles, now we're connecting enlargements and similar triangles. Really important to make that connection.
So you're saying that APQ is a triangle that's similar to ABC. It's just it's a larger version of it, but the angles are the same.
So I want to move on now to prove the ratio theorem. Now in South Africa, this is required at, for their matric in the sort of last couple of years of school. Matric is a school leaving exam. But it's something that is much simpler than other work at that level, because what you've done today, you can see this ratio theorem is a natural way of developing and using the same idea. So we're not asking you to actually do the activity right now, but if you were doing this with children, they would do the activity. What we're really going to concentrate on, well, you can do it if you want to, there would be time, and Caroline will be doing it while I'm talking. But we really want you to concentrate on the proof here, the maths here. If you're doing it with children, take much more time over it, let them do the practical steps, talk about them, and then finally, after you've worked through all the steps, go back over this proof. This basically is a formal proof of the ratio theorem. You'll see what it is as we talk. So we're drawing the triangle ABC, and you fold the baseline BC. Imagine this. Now we're wanting you to do this. You'll see Caroline doing it, and you can visualize it. So you fold a baseline BC back onto itself so that the fold line goes through the point A, and then you're going to mark the base, the point R, at the base of the fold, and we call AR the altitude of the triangle. Now you make a fold by placing point A anywhere on AR and mark the fold line PQ with P and Q on the edges of triangle ABC. Now those are not midpoints, they could be anywhere. They could be midpoints, but they could be anywhere.
I deliberately made them obviously not midpoints, but there is no reason why it shouldn't be a midpoint. But what you don't want your learners to think is that they have to be midpoints, which is why I'm really going close to point A on this.
So now what do you notice about the lines AR and PQ? By construction, they're perpendicular. What do you notice about PQ and BC? By construction, PQ and BC are parallel, both perpendicular to AR. So PQCB is a trapezium with parallel edges. Now notice, because of those parallel lines, angle APQ and ABC are equal, and angle AQP and ACB are equal, corresponding angles. And because now we've got two triangles, the pink one and the green one, half of which is hidden, part of which is hidden, we're now sure that they're similar triangles, because similar triangles, well, we met it just in the last slide, but similar triangles are different sizes and all the angles are equal. So enlargement preserves angles, keeps them the same, but the lengths change by the scale factor. What else do you notice about APQ and ABC? Well, we just said one is an enlargement of the other. Now you've proved the theorem. Okay, perhaps I should have started with the statement of it, but here it is. We've shown that PQ and BC are parallel and triangles APQ and ABC are similar. So it follows that the three ratios, here's where the ratios come into the ratio theorem, the three ratios, AP to AB, AQ to AC, and PQ to BC are equal. Each ratio, and the reason they're equal is each ratio is a scale factor of the enlargement. Now, the theorem is that if you have a triangle with a line parallel to the baseline, then you've got these ratios, AP to AB, AQ to AC, and PQ to BC are equal. That's the ratio theorem. And here it is proved by folding essentially just a simple sequence of moves, which now we should be convinced about. And you have a formal proof there. You could write the proof out without mention of the folding, and there you would have your neat, short, clear, formal proof of the ratio theorem. So if that's, well, it will be on your syllabus somewhere. It might have a different name, but there it is. Now we're going to move on to something a bit different, but nevertheless, it's starting with a triangle and folding. So I think this is a new experience and something different. And again, something that's going to be exciting for the older children in secondary school, the young adults, and it's going to be also within the reach of upper primary. For the next for drawing and construction activities. They can be done after this workshop. We'd love you to try these activities for yourselves. We'd love you to comment about what you're seeing and what you've experienced. And let's think about another area of mathematics that you can explore through folding. So now imagine drawing a triangle which this time should be cut out of cardboard.
I was going to point out, we've got cardboard, and I have been experimenting, and I've used one of those envelopes that you get from Amazon, that sort of thing. A nice thick, but not too thick.
Well, you've got your cutout triangle, cut out of cardboard for a reason that we'll find out in a minute. Now you've got to find the midpoint of each of the edges there. So find U, which is the midpoint of BC, by folding. Find V, which is the midpoint of AC, by folding. And find W, which is the midpoint of AB. Now, draw in your fold lines. These are not the fold lines you've just made. Those were to find the midpoints. Now draw in the lines A, U, B, V, and C, W. And what do you notice about these? They're called medians, by the way. What do you notice about the medians that you have found by folding? So Caroline's drawing them, okay? And she's going to demonstrate this. And now you'll see why we've done it with card. This is amazing, is it? or did you expect it? Caroline is going to balance this triangle on a pencil point at G. G is the point where these medians intersect. That point's called the centroid, or the center of gravity of the triangle, by the way.
Which I did earlier, no problem. I did it straight away, but I've got a bit of, it does work. It really does.
Well, there you go. There's something for you to try. So now the next one is the altitudes of the triangle. Now you draw the triangle again, which can be cut out. You fold to find AU, which is the perpendicular line from A to the base. And you call that an altitude. And you repeat to find the other altitudes, BV and CW. And what do you notice about the altitudes that you found by folding? Well, the picture shows you.
I'm not sure.
And you've got a long, thin triangle, which makes it a bit difficult.
It makes it very difficult.
Anyway, if you draw the altitudes, which are the perpendiculars from the vertices to the opposite edges, there they are. They also, all three of them go through the same point. And there's no reason to be, in advance, unless you've seen it before, there's no reason why they should go through the same point. A, U, and B, V might intersect in one point, and A, U, and C, W in another point. But they are what we call concurrent. They are all cut in the same point, H. We're going to move on to the perpendicular bisectors of the edges of the triangle. It's a different one. Now, for good reason, when you do this, don't cut it out. Do it on a piece of paper, and this is where you're going to use your compasses. Now you fold to find U, which is the midpoint of BC.
That's wrong.
And you can mark that fold line now. All you do here is you do the perpendicular bisectors of the edges of the triangle. And as before, you'll find that they meet in a single point. And we've done these finding the midpoints before. So the midpoint of BC is U, the midpoint of CA is V, and the midpoint of AB is W, and there are fold lines there are now.
But they're not
shown.
coming together on mine, Tony. That's the problem. Their point of intersection is outside the triangle.
Ah, okay, okay. But they will meet outside the triangle or inside the triangle.
Okay, right. I'll do. Okay, so they don't have to meet inside the triangle. So
No.
that's a useful little bit of extra information that I didn't have.
And in fact, if you do this with a class, and some of your class have done what Caroline has done, you see, she's doing it with a cutout triangle. Caroline, it says there, don't cut this one out.
It does. It really does say don't cut it out. And
so you would still find that the points, sorry, the perpendicular bisectors met at a point, but it would be outside the triangle. Why are we doing this? Well, this is very interesting. We want to explain why all the points on the perpendicular bisector are equidistant from B and C. Well, you might say that's what a perpendicular bisector is. You'd be right. But if you take any point D on that red perpendicular bisector, then join DB and DC, what do you notice? We've got the two right-angled triangles making an isosceles triangle there. Those are congruent and DB equals DC. And that happens for all points on that fold line. Now, if you label the intersection of the perpendicular bisectors as O, whether it's inside or outside the triangle doesn't matter, with your compass point at O, draw a circle center O that goes through A. And you can do it whether your O is inside or outside. But what you're going to see with Caroline's is that it's outside. What do you notice about the circle? There it is. It's going through A, B, and C. It's got a center at O, and it's called a circumscribed circle. Circum means around, scribe means written. All right, this is Latin, I think.
Well, it still works. And I'm glad I'm demonstrating it this way, because now you know, now you really know that it matters.
And I think for your learners, your students, it will be a nice surprise that you do all this down to 0.8. Then you see that the circle will go through B and C. John has asked what happens when the intersection O is on the line AC for the circle and the triangle. You can think a bit more about that. That's interesting. My goodness, I like that one, John.
I think I mean BC there actually, but yeah.
Yes. And of course, if O is on BC, then you've got, then BOC is a diameter. And you've got, well, a lot more that you can see then. Now I want you to explain why this construction gives you the circle through A, B, and C. If you go back to the diagram on the left-hand side, you'll see that everything that's applied for the red fold line, that red perpendicular bisector, also applies for the green one. So you would have DC equals DA, and bingo, you've got the three radii being equal. We have another one. And here you draw the triangle ABC now, which can be cut out, and you fold through A so that AB goes on to AC, and you repeat for B and C. Imagine it. What do you notice about the angles? What do you notice about the fold lines?
Sorry, well, it says it at the top of the page.
Oh, it does say it at the top of the page, that angle bisectors. This is the fourth center. It's the last one. So what we have got here is the three angle bisectors, and they again meet at a point. And now we go on. We label the intersection of the angle bisectors as the point I. And with your compass point stuck at I, you draw a circle center I, and this time it's just got to touch the edge AB, and you label this point X. Pam says it's much harder to fold the angle bisectors. Yes, it is.
A really tight angle like this one.
Well, the thing is, you've got to make the fold go through the angle. It's easy enough to make the edges coincide somewhere, but at the same time, you've got to make the fold go through the vertex of the triangle. And the whole point about the construction lines is we're showing you that it can be done by folding. It just takes time and care. Everything here can be done by folding. And Caroline's showing you that this is the inscribed circle. The last one was the circumscribed. This is the inscribed circle that you get. And it touches all the three edges at points X, Y, and Z as you've seen them here. And now the big question is to explain why this construction gives the inscribed circle. Why is IX, IY, and IZ, why are those three equal? Why are they all the radius of this inscribed circle? And here with your 17-year-olds, you know, there's some maths, there's some geometry here to some understanding of the maths to explain here. But it's an experiment that they can do, investigation they can do, not at the speed we've done it this afternoon. So look here now at this answer number 9. Can you see it now? You've got those purple lines in. Okay. Now you've got pairs of congruent triangles in those three kites. And with a little bit of care about the way you do it, you can explain that AX and AY are equal, and then BX and BZ are equal, and then CY and CZ are equal. And now you've got a circle theorem about, from an external point to a circle, the tangents are equal lengths, right? So because AX and AY are equal, I know that, looking at this diagram, that those two triangles are congruent, AXI and AYI. I know that AXB and AYC are tangents there, and just touch, and those are right angles. Okay, there's a lot of maths in that, a lot of geometry.
It also shows what, you know, you talk about the tangents of a circle, and this is an application. This is somewhere where you actually use those bits and bobs you learn about circles, and then hey presto, you're doing construction like this and you're actually using them.
So if you're talking about some major public examination, could be the school leaving exam, where there's some geometry, this is a lovely activity to revise all the geometry that they have already learnt, but to remind them of it. And by asking them questions about what they're doing, these 17-year-olds, or then they're going to come up with answers. And here you see the 4 centers in one picture here, and the 2 circles, the inscribed and the circumscribed circles. So that's just a summary of these, finding these centers of the triangle. They've all got special names. We talked about the centroid for the medians. For the altitudes, it's called the orthocenter. For the angle bisectors, it's called the incenter, and for the perpendicular bisectors, let's give you the circumscribed circle. It's called the circumcenter. There's lots more maths that's beyond this, the 9-point circle. And I looked it up, John, this idea about the conics, which is a generalization of the 9-point circle idea.
I thought it might be.
Okay, so now this is our opportunity to summarize what we've done in this workshop. We really want your comments. We really want your questions that you might ask other people that go beyond what we've talked about, not necessarily beyond them in the mathematics, but more ideas for teaching perhaps. So please, please, please contribute here to the discussion. On the Aiming High website, there are some resources here for these activities. Also, we mentioned the Aimsec resources, Aiming High resources, and that's where you'll find them. We also encourage you to share ideas with other teachers, and there you'll find on the Aiming High website the links for that, for collaborative professional development and how to manage your own workshops with other teachers. And then this is the last slide before we say goodbye. And here you'll see where to find the free lesson resources, the aiminghigh.aimsec.ac.za, and the collaborative professional development that I just mentioned. How to find the app to download the resources and to use offline. The Aimsec website tells you more about the organization, Aimsec, my email, Caroline's email. Now you can inquire about signing up for an Aimsec course as a self-funding student if you want to do that. And then finally, thank you for participating. And goodbye until the next GTEN workshop.
This is a Global Teacher Empowerment Network video collaborating with Aimsec and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.